I'm thrilled to be here. I've put together a presentation that sort of summarizes a body of work that's somewhat large and scattered throughout the literature. It's a collaborative effort between a large number of people, both here at Los Alamos and external to Los Alamos, and it takes advantage of experts in a wide range of fields: synthesis, spectroscopy, theory, and radiochemistry. And what we've tried to do is assemble a team who have a very different perspectives and try to advance general understanding on the role of f and d orbitals in covalent bonding for actinide elements. So let's see if this is going to advance. Oh, here we go. I got it. So the actinide elements, these are a unique group of elements that occupy central roles in numerous areas that are directly impactful on our quality of life. Okay, and that spans from being used as medicines to being central components to national security. And what I believe is that in order to solve technical problems in all of these different areas, you need to understand fundamental characteristics and properties of those actinide elements. And one of the properties that I want to talk about today, as I said earlier on that goal statement, is that associated with covalency and bonding. This is a topic that has been studied and discussed and debated for decades. And I've tried to summarize those discussions on one slide, which is virtually impossible. But I've included here a series of key references that I think are important. The other thing I've done is I've tried to summarize what I think the community believes with these two graphs that come out of this Cross white paper from 1980. These graphs, I'm plotting the radial distribution of the valence orbitals and then the core orbitals, okay, as a function of distance from the nucleus. And I've done this for uranium, okay, in the +3 oxidation state, and then I've also done it for the lanthanide that's right above uranium. This is neodymium. And what you see is that as you move away from the nucleus into this bonding region, somewhere between 2 and 3 angstroms, the core orbitals for neodymium, they extend beyond that of the 4f orbitals. The 4f orbitals are buried within the core. That's for neodymium. In uranium, the situation is somewhat similar, except the 5f orbitals, they peak out just a little bit, okay? So they're a little bit more available for bonding in a covalent way. What these types of calculations and other calculations and observations similar to this have led the community to conclude is that the 4f orbitals have limited spatial overlap, and what that means is that they're not very accessible to form covalent bonds. That's also led people to conclude that the d orbitals are the primary contributors to covalent interactions between an actinide and a ligand. And what we've been trying to do is better quantify the relative roles of the 5f orbitals for an actinide versus the 6d orbitals. And I think the technique that we thought provided the best opportunity to do that is one called Ligand K-edge X-ray Absorption Spectroscopy. Okay, this is essentially just a Zane's measurement, but instead of doing an excitation on the metal, we've been doing excitations on the ligand. Okay, in this case of titanium hexachloride, that would be chlorine. This over here on the right, this is a typical Zane's measurement at the chlorine K-edge for titanium hexachloride 2-. This is titanium +4. I want to just walk through a little bit of detail on this so that we're all on the same page. I know that this may be a little bit too rudimentary for this audience, but let me just walk through this because I'm going to show a lot of these types of plots, and I want to make sure you understand what I think is important. Okay, so I'm plotting normalized intensity on the y-axis, and I'm plotting energy in electron volts increasing from left to right on the x-axis. Okay, and in a Ligand K-edge X-ray absorption measurement, we start at low energy, and we increase the energy of the excitation source, and eventually you move into this pre-edge region where you have bound state transitions, okay, where you're exciting a a chlorine 1s electron into an antibonding orbital that results or exists because there's covalent bonding between the metal and the ligand valence orbitals. Okay. When you go up higher in energy, you start to access the edge transitions where there's these excitations into the chlorine 4p and the 5p and the 6p. Eventually you ionize the absorbing atom and move into the XAS portion of the spectrum. We're interested in this pre-edge region, okay, for a couple of reasons. The intensity of these features is directly related to the amount of chlorine 3p character in this antibonding wave function. Let me say that in another way. Because that core hole is localized on chlorine, and because these are dipole allowed transitions, S to P, you can measure this intensity and quantify the amount of orbital mixing. If there's no orbital mixing, a completely ionic interaction like in sodium chloride, this orbital doesn't exist and you get a flat line here in the pre-edge region. But if there's a lot of orbital mixing, like in the case of the titanium chloride bond, you can see these pre-edge features, and they tell you not only about the ligand field, they also tell you about the mixing coefficient. And Ed Solomon and Britt Hedman and Keith Hodgson, they've done a lot of work to demonstrate how you can use this technique to quantify orbital mixing in bioinorganic systems and inorganic systems. And what we've been trying to do is expand on their efforts and apply this technique for quantifying covalency in actinide systems. What I'd like to show you today is a number of measurements that we've made on metal hexachloride compounds. Okay, we selected these compounds for a couple of reasons. The octahedral molecule, okay, or a metal complex in an octahedral symmetry, those have been foundational for developing the way inorganic chemists think about bonding, okay? And so we thought this would be a good place to start with the actinides. The other thing is, in octahedral symmetry, the f and the d orbitals, they can't hybridize, so you can discretely probe the 5f orbitals or the 6d orbitals. Most of these compounds are pretty air and moisture stable, so that facilitates being able to transport them to a synchrotron and do X-ray absorption measurements. They're also basically a ubiquitous structure. That means that we can look at a metal octahedron and change this metal, okay, with 6 chlorides around it, and we can walk across the periodic table and try to understand how covalency changes as a function of metal identity in the same ligand environment, and then we can also change the oxidation state of that central metal and try to understand how oxidation state changes also impact orbital mixing. So let me just come back to this first spectrum I showed you. This is again this titanium hexachloride complex. It's a dianion. Okay. You see 2 pre-edge features. Okay. They're attributed to excitation of the chlorine 1s electrons into the T2G. Okay, this is a pi bonding orbital. Okay, and then there's also an excitation into this sigma orbital. Okay, and we can quantify the orbital mixing between chlorine and titanium in this system, and we can tell you that there's more sigma mixing than pi mixing. Okay, the covalency is larger in the sigma orbital than in the pi orbital, and that's what you would probably expect. We can switch. Or what we did next is we switched out this metal, okay, and we started walking from titanium, a third or first row transition metal, down towards the actinide series. Okay, here's this system here: titanium 3D, zirconium 4D, hafnium 5D. They all have 2 pre-edge features, but what you notice is that these 2 pre-edge features, they march to higher and higher energy as you go down the periodic table. That's consistent with what you'd expect for those relative 3D, 4D, and 5D final states. Okay. We can't quantify the amount of sigma covalency in the sigma bond for each one of these compounds, because as you can see in hafnium and zirconium, that transition starts to walk into the white line, but we can evaluate the pi mixing. Okay. And we can see that the pi mixing seems to be increasing as you go down the periodic table. The next spectrum I want to show you is that for uranium hexachloride. Okay, so those are titanium, zirconium, hafnium, then uranium. And when we first made these measurements, we thought that we may not see any pre-edge features because the lore was that the actinides did not participate that much in covalent bonding. And we saw these two features here, okay? We walked back from the synchrotron and we said, look, here's T2G, here's EG. We think there's no F contribution to bonding. And our theory collaborators, Ping Yang and Enrique Batista, they ran some calculations and they said, no, they did not think that was the correct interpretation. What they said is that, you know, here's the T2G and EG orbitals that I was talking about earlier. They said you needed to consider the 5F manifold. I've drawn it in here. I've got the bonding down here and the anti-bonding up here. They said that this low energy feature was an excitation of chlorine 1s electron into the 5F manifold. And that here was the T2G, and then EG, just like hafnium, they said was buried under the white line. So the way that we solved this is we arm wrestled to see who would be right. No, we did a whole series of experiments to try and understand if that was correct or not. And I haven't told you exactly how it worked. We really made the titanium, zirconium, and hafnium measurements afterwards to try and help us understand this spectrum that we first obtained. And their interpretation, I'm just going to, spoiler alert, it's correct. I'll show you some experimental validation for that interpretation. The first thing you can do is you can think again about how these two transitions are moving as you go down the periodic table. Look, T2G, here's 3D, 4D, 5D. It makes sense when you go to 60 at uranium, it goes up in energy. That's what you'd calculate. Look, titanium, T2G, 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 T2G. And then what appears, what's different about the uranium is the 5F manifold falls in at lower energy, okay? That intuitively makes sense, and it's consistent with the ground state calculations that I'm showing over here. I'll show you another experiment that I think is the clincher, okay? It's actually a series of two experiments. Like I said, we have synthetic chemists on the team, and what we realized, okay, this right here in the middle, this right here, this is just that orbital picture I showed you earlier. Here's the 5F orbitals in red, here's the 6D orbitals in blue. And what we realized is that if we just took one of these chlorides and we substituted it for an oxo, we would reduce the symmetry and split these orbitals out, okay? And what the theorists predicted is that in this situation, okay, for the octahedron, they were saying you got two transitions. For this molecule here in C4b symmetry, they said, well, there should be 1, 2, 3, 4, 5 transitions, okay? And it should be dominated by this orbital here, which they calculated would be highly covalent. It involves this axial chloride ligand that forms a very covalent interaction with uranium due to the inverse trans influence. This bond right here is 1/10 of an angstrom shorter than these equatorial chloride bonds, okay? And what we saw experimentally, okay, look, 1, 2, 3, 4, 5 peaks. You cannot rationalize 5 pre-edge transitions if you only invoke the d orbitals. There has to be 5F character, 5F orbital mixing happening. And the other thing, look at this huge peak right here. This is attributed to this feature right here, this axial chloro. I can turn it off. I can remove this chlorine and put an oxygen here and watch what happens. This peak's going to go away. There it is, it's gone. Now you just have 4 features when you go to uranyl. 1, 2, 3, 4. And this right here is due to 5F, and this right here is due to 6D. So what I've been trying to do to this point in the talk is just communicate that we have a very good understanding of how to interpret these chlorine K-edge X-ray absorption spectra, and that we can discretely interrogate 5F bonding versus 6D bonding. And what I'd like to do now is think about how 5F and 6D orbital mixing changes as you go across the actinide series, still in this octahedral hexachloride compound. I'm going to keep the oxidation states the same. We're going to be plutonium 4, neptunium 4, uranium 4, and thorium 4. We're growing single crystals of these compounds, so we know the samples are very pure, okay? And we're just going to walk across the actinide series here, okay? And I'd like you to think about what we observe in the context of this equation here. This equation shows you that covalency, or the mixing coefficient, it's directly proportional to the spatial overlap of the orbitals involved in a metal ligand bond. So it's the spatial overlap between the ligand orbital and the metal orbital. Okay, if that's large, you get a large mixing coefficient, you get a lot of covalency. And I'd also like you to think about this denominator. Okay, this tells you that you get a large mixing coefficient if the energy of the valence orbitals for the metal are matched with that of the ligand. Okay, if they're matched, then this denominator is small and you get a large mixing coefficient, you get a lot of actinide ligand covalency. Before I show you the spectra, I just want to provide you with a molecular orbital picture that helps you think about what we should observe experimentally. Okay, so these are some calculations for the valence orbitals of thorium hexachloride versus uranium hexachloride versus neptunium hexachloride versus plutonium hexachloride. And what you see, okay, these circles right here, these represent the unpaired electrons. But what you see is that for thorium, the 5f and the 6d orbitals, they're close in energy, okay? And then as you move across the series, the 5f orbitals, they drop in energy and they spread out. And the 6d orbitals, they stay relatively in a narrow energy range and they don't change in energy, okay? And so if you were to think about excitations from a chlorine 1s electron into these orbitals, you'd think that maybe you have one peak here, and then the transitions to the D features, those stay relatively constant, and the 5f orbitals, they broaden out and drop in energy. And that's exactly what we see. Here's thorium, one transition. Uranium, I showed you that earlier. There's two transitions there, a D and an F. And then you see that F manifold, it drops in energy and it spreads out. This is exactly what they predict when they do TDDFT calculations. Okay, F and D are right here, and then you see the F fall out and spread out. Okay, D remains relatively constant. I'd like to go into more details about what we about what we can extract from these measurements, but I don't have time for that. So I'm just going to talk to you about some general trends. Okay, and this is a complicated graph. Okay. But I'll walk you through it. On the left here and in orange, I've got the calculated oscillator strengths from the time-dependent density functional theory calculation. Okay, I could have plotted the Mulliken populations and you'd see the same thing. Okay, but what this tells you essentially is that the theorists are predicting that as you move from thorium to uranium to neptunium and plutonium, the 5f orbital mixing is increasing, and the 6d orbital mixing in the T2G orbital is decreasing. And then in blue over here on the right, I've got the experimentally derived peak intensities. Okay, and you see that the uranium, it goes up for the 5f's. This suggests that plutonium chloride bond is more covalent than the uranium chloride bond, at least from the perspective of the 5f orbital mixing. And you see that the 6d, it's decreasing. Okay. The 6Ds are getting less covalent as you go across the series. I can explain why in 2 slides, if you give me a chance. Okay, the first one's here. This is another one of these plots that shows radial distribution of the orbitals versus distance from the nucleus. Okay, and I've got 4 traces on here. I've got thorium in blue, uranium in light blue, neptunium is in this ugly brown, and then plutonium's in red. And what you see is as you go across the series, thorium to plutonium, what's happening is you're increasing the effective nuclear charge on that metal, and you're collapsing the valence d orbitals. They're getting less radially extended. Okay, that means S is getting smaller. They're less available for covalent bonding. Same thing's happening for the F's, but these guys are core-like. Okay. So I don't think that this term is that important for the F's. What I think is important for the F's is the energy of those valence orbitals. Now this is a calculation Enrique Batista ran. It shows the energy versus the metal identity for the entire actinide series. And this is for the actinide atoms in the 0 oxidation state, okay? And what you see is, like I showed you earlier, the 6Ds, they stay relatively constant. The 5Fs drop. I think that dropping is moving them closer to the chlorine valence orbitals. and it's turning on the mixing coefficient because of this idea of an energy match between the metal orbitals and the ligand orbitals. We're calling this energy degeneracy driven covalency. So what I've tried to show you is that you can rationalize whether you're getting covalent d orbital mixing or covalent f orbital mixing by thinking about this equation. And what we're seeing is for the 5f's, as you move across the series, you're pulling the energy of the metal valence orbitals down, and that's providing energy matching, energy degeneracy, and that's turning on orbital mixing. The next part of this talk, I want to discuss how oxidation states impact that, but maybe this is a good time, Jerry, if there are questions.
Yeah, there's a few questions. First, in an earlier part of the talk, you showed the progressive energy shifts for the EG and T2G as you went from titanium progressively to heavier and heavier metals.
Sure.
Do you have a qualitative explanation for why, in general, as you go to the heavier metal, those states should be smoothly shifting upward in energy?
Yeah. Can you ask that second part one more time?
Yeah, you've got a monotonic trend here, increasing energy with increasing Z of the metal.
Yeah.
Why?
So I think that has to do again with this, you know, qualitatively, I could show you this picture right here, and
Yeah.
as you go 3D, you're going to be down low in energy. When you go 5D, that's going to be up here.
Oh, I see.
You're going to push that up. Now you can see, if I could show you one more plot, I don't know if I can do this. I'm going to try. Hang on one second. You can see that optically using UV vis. So here, let me see if I can display this. So that's known. This is a nice correlation as well. What I'm plotting here, okay, I'm thinking about this interaction, laser pointer. I'm thinking about this transition, exciting a 1s chlorine electron into the T2G manifold, and I want to change the metal. And I'm plotting the energies from the X-ray absorption versus the ligand to metal charge transfer excitation. So that's exciting here at the T1G from chlorine. And what you see is the exact same trend. As you increase the energy here, you push this orbital, this T2G orbital, up in energy, and there's a linear correlation between hafnium, zirconium, and titanium. Okay.
Okay, that does make sense. Thanks. You want to go back to the main presentation? I'll let you flip that, and then Matthew Marcus, you can unmute your mic, but give Stosh a second to get the slides back up again.
I think this is where I was. Is this where I was? No. Does anybody remember where I was in this?
Yeah, you were at the slide where at the bottom, that one. Yeah, you were at that one. Matthew, your question, please.
Yes. Yeah, you mentioned that you make single crystals of these things, and that seems to present an opportunity, which is that by using polarization, you could selectively weight, say, the axial ligands or that A1 transition that you talked about. So I was wondering if you were using that and getting some more information.
That's a great question. There was a little bit of information that I didn't tell you. I'm going to come back to this slide, and I just want you to think about this structure. This is a weird cation, tetraphenylphosphonium. It's a big organic cation, and what we selected it because it's non-interacting. There's like 10 angstroms maybe between this actinide, or excuse me, the chloride, and the carbon associated with the phenyl. There's absolutely no interaction. And we do that on purpose because we just want to be able to probe the actinide chlorine interaction. The downside of that is that it doesn't line these anions up well in the crystal, and so they're distributed wildly throughout the lattice. So we can't do a polarization experiment. When we make these samples, we grind them up, okay, and we distribute them and we suspend them in we suspend them in a little bit of boron nitride, and we paint them on some tape to try to make sure that they are randomly oriented in the beam. There are other compounds that we have looked at where we have done some polarization studies, and we're about to publish that.
Yeah, do you do these measurements in transmission then, or fluorescence?
Fluorescence.
Okay, so I guess you have to deal with overabsorption because penetration depths are pretty small and down at chlorine.
Yeah, so they're very dilute. These measurements are made on very dilute samples. We've quantified, or at least we've demonstrated that we don't have self-absorption with the fluorescence measurement. So there was a lot of work that went into that. And then the other thing you bring up is that the containment strategy for these radioactive samples is a mess. So we've got a 4-micron window on the sample, mylar or polypropylene, and then that's in a chamber that it's our own special chamber, and that has you know, that's under helium, and that's isolated from the beam with a beryllium window. So there's 1, 2, 3 layers of containment for each one of these samples, but it has to be transparent at 2800.
Yeah.
It's a drag. It's a drag. Transmission is not an option. We can't blast through the sample. We can't get through it. We can't get fluorescence.
Yeah, TEY might possibly be an option.
All right.
Yeah.
We've struggled with that. Yeah.
One last question for this break from Alex Ditter.
Hey.
Who invited him?
Hi.
I thought I took you. I thought I got rid of you.
You tried. So one thing I often hear from people is that this orbital mixing is great, but if the electrons aren't actually shared between the metal and the ligand, like if the electron density is all around the ligand, then it's not really a covalent bond. Do you ever look at the TD-DFT, like at the bound states that they calculate to see if the electrons are actually shared between the atoms here, or is that something you guys haven't looked at?
Absolutely. So we will look in the excited state and in the ground state. But Alex, you know, I mean, that's one of the things I hate about this topic is the word covalency. It's a lightning rod, and it
right.
evokes emotions in people. And that's why I've tried to be very systematic about how I've defined orbital mixing. And I'm doing that in the London sense, okay? And I'm defining it by this equation. And so I'm trying to get away from these terms, polarizable bond, or, you know, and just, and think about covalency in its purest form, if you will. And I know that's going to mean something different to everybody in the room. But there are people, like you say, that want to think about covalency just by thinking about this numerator. And I think that if we can identify situations where large amounts of covalency lead to differences in behavior, then all of a sudden we've solved that problem and said, yes, this is an important metric.
Right. Okay, that makes sense. Yeah. Thanks.
One last question, Christina.
Oh yes. Hi everyone.
Christina, good to see you.
Thanks a lot for. Yeah, exactly. I'm unfortunately in the car driving back from work, so
I'm driving
but
too.
I just parked to because I was following your exactly. Stosh, excellent talk and excellent examples. I just wonder, you know, by hearing your story about the uranyl compound, you know, if I look at your data at the chlorine age, it seems the separation between uranium 5F and uranium 6D comes in order of 2 electron volts, right? I mean, this is what I saw now on your slide. I just wonder, you know, if you measure L3 age of the uranyl compound by high resolution spectroscopy and spectrometer, you can really resolve clearly the pre-age structure and the main age, where with some kind of belief, right, where the pre-age is due to the quadrupole transition between 2p5f and 2p6d, and where the separation comes in order of, I think, 6 or 8 EV. I don't remember now, and unfortunately, I don't have the paper next to me.
No, you're right.
I just wonder, do you have any reason for that? Why in chlorine age this separation is smaller somehow for compared to the L3 age?
So, Christina, let me try to just communicate a couple of things. What you're seeing is you're seeing this difference here between this manifold, okay? Oh, hold on, where am I? You're seeing the difference between F pi and F delta and F phi with that D pi. There's more transition. Yes. The A2U is way up here. We don't resolve that.
I see. I see.
And you know, we made those M-edge measurements. Oh, I think we saw that uranyl post-edge structure. I don't know, back in 2000, when I first met you, I was showing that M-edge data to Tonya. And I said, the reason we never published it was because we thought that peak splitting was too large. It didn't make any sense to us. But you guys figured it out and put that in the literature, and it's great. I do believe, and I have no data, so I'm just making stuff up right now, but I do believe that there's some substantial final state effects associated with putting the core hole on uranium that spread those transitions out. But I don't have any scientific evidence to corroborate that idea.
Yes, I in fact I was talking about L3H, not MH, because I on separation of the pre-H and the main H. But I see now, so I didn't see on your figure further transition, so maybe I have to read it a little bit more. Stosh, thanks a lot. Great talk. Thank you.
Oh, I appreciate it. Yeah, you bet.
All right, you should move on to the next part of the talk, Stosh.
Yep. Okay. Here we are. Okay, so I'd like to start thinking about how oxidation states impact this orbital mixing coefficient. I'd like to come back to this uranium hexachloride spectrum I showed you earlier, okay, where we think we have the 5F here and the 6D here. What we're going to do next is we're going to oxidize uranium from +4 to +5. And here's just a picture trying to communicate to you that we can do this quite well. These are crystals of this compound, and this is uranium-5, okay? Same geometry, okay? Here's a comparison of the two spectra, and what you notice is that this D peak is a little bit lower in intensity, and then this F peak is huge. That suggests a lot of covalency in the uranium-5 chlorine interaction that's not present in the uranium-4 chlorine interaction. I'll show you another example. For this one, I want to think about lanthanides, okay? Here we can change from cerium-3 to cerium-4, okay? So we can evaluate the same concept, what happens to covalency when we change the oxidation state of the central metal, and I want to compare that with the +3 lanthanides, neodymium, samarium, europium, and gadolinium. Okay, I'll start with the +3s, and then I'll show you the +4 spectrum. This is the spectrum of cerium hexachloride with 3 in the 3+ oxidation state, okay? And here, up here is the 5D peak, and this one in red, that's the 5F peak. Now I'm going to change the metal center and walk across the lanthanide series, but I'm going to keep the oxidation state the same. And what you're going to see is that this big peak, it gets lower in intensity, and then you'll also see that this little red peak, that also gets lower in intensity, okay? And then it's going to shift to the right until we get to gadolinium, and then it's going to disappear, okay? Let me show you that, okay? And just to help you see it, I'm going to hold my cursor right here, okay? So here's cerium, there's samarium, everything got lower. Here's europium, there's gadolinium, it's gone, okay? That's the 5F peak. 60 peaks getting lower, the 5F peaks dropping in intensity and going away. Here's an overlay of all of those spectra. You get this little 4F peak, and it kind of goes out here and disappears. T2G peak, it gets less intense. Look what happens when you oxidize the cerium from 3 to 4. This gets huge. Here's another representation of that. Okay, here's that little 5F business, excuse me, 4F business for the +3s. Look at how big that is. Covalency and lanthanides, that's unusual. Here's a cleaner representation where I'm just comparing the +4 cerium 4 hexachloride with the +3 cerium 3 hexachloride. You see there's absolutely nothing, no business down here for the 4Fs, and here's the 5Ds. I'll explain to you what I think is happening with those two examples, the uranium example and the cerium example, okay? And I think it's all related to this energy degeneracy-driven covalency concept. For cerium 4, you have the 4F orbitals. They're high in energy. They're core-like. There's energy mismatch with the chlorine valence orbitals. Okay. When you go cerium 3+ to cerium 4+, you drop the energy of these 4F orbitals, and now you have energy matching, and you get this swamping 4F peak. When you go cerium 4 to uranium 4, 4F to 5F, that pushes them back up. Now you have a little peak, okay, that's here. And then when you go uranium 4 to uranium 5, that pulls it back down again, and you turn on the 5F covalency. For uranium 5, you've got the 5F covalency turned on. When you go to uranium 4, you turn off the 5Fs. Cerium 4, F on. Cerium 3, F off. That was a joke. So what we're saying here is that you can move this up and down by changing the oxidation state of the metal, and high oxidation states are going to pull the orbitals down and make them well matched in energy with the chlorine 3p orbitals. Does that make sense? This energy degeneracy driven covalency concept. Okay, I'd like to now think about what we're seeing. Okay, as we move across the actinide series, we turn on covalency. When we increase oxidation state, we turn on covalency with the 5Fs. What happens with the minor actinides? Okay, so we're going to go one more step to the right of plutonium. That should turn on f orbital mixing, but americium isn't very stable in the +4 oxidation state. So we're going to drop the oxidation state down to +3, and that should decrease covalency. And we didn't know which concept was going to be more important. When we go to americium, is its position along the series more important, or is the oxidation state more important? So we had to make this compound at the time. This is a single picture of the single crystals of americium. At the time when we published this, there was, I don't know, not very many examples of americium structures. Okay, there was 13 entries in the Cambridge database, and there was 110 in the inorganic database. Okay, and here's the paper right here. Okay. So I just highlight that in terms of stamp collecting, that was an achievement. We didn't make it because we could. We made it because we were trying to answer a scientific question. And I'll show you the chlorine K-edge X-ray absorption spectrum of americium on the next slide. And what you're going to see is that the americium hexachloride spectrum looks a lot like the europium spectrum in that the 5F peak is very, very small. Okay. There is a lot of structure on this orange trace that's associated with the americium chlorine K-edge spectrum. And I put the second derivative of the data down here so that you can see that our interpretation makes sense. Here's that europium 4F peak. Okay, you can see a negative peak in the second derivative. That shows you that there's a feature here. Okay, when you go up in energy, 4F to 5F, that's what you'd expect. And then here's 5D, that's this feature right here. You can see that. And then when you go to 6D, higher in energy, that's right here. Okay. The curve fitting analysis is on the next page. You can't fit this data very well without including this little orange peak. Okay, that's due to americium 5F orbital mixing with chlorine. On the europium side, there's the 4F peak. That's very, very small. You can fit this and ignore that if you want. Here's the calculations from the TDDFT simulations. Sorry. And you see they predict 5F down here and 4F over here, and here's the T2G peak. We can do our curve fitting analysis and we get an error bar on that peak area at, I don't know, about 10%, we can deconvolute this spectrum and we get an error bar for that 4F peak, and the uncertainty is 300%. Okay, so we can't quantify how big this is. We know it's small, and we know it's there. This one we can quantify, and it's about 0.54%. That's nothing, right? There's very little 5F covalency in that americium chlorine bond, but it's more than what you see in the europium case. And I think the frontier right now is, how do we design systems that turn on the 5F covalency in the americium ligand interaction? If you could do that, I think you could solve some technical problems associated with americium. But the first step was to be able to make the measurement and interpret the data, and that's what I'm trying to show you here. And in terms of the overall scientific question that we started out, I think we know what the answer is now. The oxidation state seems to impact or be more important in terms of orbital mixing than where you are along the series. When you go to +3, you at least turn off the 5F orbital mixing with the metal chlorine interaction. There may be other ligands where you can turn that back on, but at least with chlorine, it's turned off. And so now, Jerry, I'd just like to summarize, if it's okay, and then we'll open it up for some more questions. I'd like to summarize with this thought. If you think about the structures of all of the metal hexachlorides that I showed you earlier, and there's some on here that I didn't show you spectra for, but what I'm doing here is I'm plotting the average metal chlorine bond distance versus the ionic radii. And what you see is that all of these line up right on a line, okay? And that the y-intercept is pretty close to what you'd expect for the chlorine ionic radius. What this means is that you can predict the bond distance using ionic concepts, ionic bonding concepts. And that might lead you to believe that the electronic structure for all of these compounds are similar and that the orbital mixing is similar, and that's not true. What I showed you is that it's wildly diverse, despite having, despite being able to predict the metal ligand bond distances based on ionic concepts. And what I'd like to do now is I'd just like to summarize everything I've shown you, and I'd like you to think about it in the context of that equation. And I'll pop that back on here in a second. But what I'm showing you on this plot is the amount of chlorine-3 character in two different metal ligand interactions. The D pi orbital, okay, and then total F. Okay. And the first comparison I'd like to make is what happens when you go down the periodic table, okay? And again, here's that equation I want you to think about. And what you're going to see is that we believe that this orbital overlap term is very important when you think about covalency for d orbitals. So here's 3D titanium, here's 4D zirconium, it's getting more intense. Here's 5D cerium and hafnium, they're similar and they're more intense. And then when you go to uranium, it gets bigger. And that's because this orbital here associated with the metal is getting bigger, and it can reach out and touch the pi orbital of the ligand more effectively when it's a 6D orbital than when it's a little tiny 3D orbital. So S is important. When you go across the lanthanide series, you increase the effective nuclear charge on the central metal, and that contracts the d orbitals, okay? And so you see as you go across the lanthanide series, we see the d orbitals are getting smaller, and the 5D contribution to covalency, that also is getting smaller. Same thing happens in the actinides for the 6Ds. These get smaller and smaller because the numerator is important for these valence orbitals that extend past the core. But for the 5Fs, the situation is different. For the 5Fs, if you hold the oxidation state constant at uranium-4, neptunium-4, and plutonium-4, you see an increase. That's counterintuitive if you only think about the numerator. But what I've told you over and over again is that you're getting better energy match with chlorine 3p, and this concept of energy degeneracy-driven covalency is pushing or turning on covalent mixing within the same oxidation state for the 5F orbitals. And then you can do that in a more extreme way by changing the oxidation state. Sorry, I should have told you this. That's because these things are core-like. The numerator is not important. You can turn on covalency to a more extensive case by changing the oxidation state of the metal. Look at this, 5F, uranium-4. 5F, uranium 5. Cerium 3, 4F, cerium 4, 5F. Americium 3 is going to be small. So with that, I'll just conclude and I'll tell you that what we've observed is that the d orbital mixing seems to be dominant, the dominant interaction for covalency in terms of metals in the +3 and the +4 oxidation state for actinides and the +3 and the +4 oxidation state for lanthanides. I've shown you over and over again, and there's a lot of examples of this in the literature, that d orbital mixing seems to be heavily governed by the numerator in this relationship. But then I introduced this idea of energy degeneracy driven covalency and tried to communicate that that seems to be what's important, or at least that's what we propose is important for these core-like f-orbitals. Okay, but this denominator is something you should think about. And I don't think that that is a radical concept, and I think it actually fits quite nicely with what the community thinks about when they think about f-orbital covalency. Remember, I told you that these 5 f-orbitals, they do not extend very far past the radon core. So S can't be that important, okay? But the energy match seems to be. And with that, I'd just like to conclude. This is a photograph of a team, okay, in a very safe configuration, okay? I'd like to thank them for their contributions and all of the people that have worked on this project in the past. I'm grateful to SSRL for working with us. We were making some measurements that I showed you here on pretty radioactive samples, and they were in pretty large quantities. I'm also grateful to the heavy element chemistry programs for support of this research, and also the Office of Science for supporting students. They've been quite generous to us and funded students to come and spend an entire year working on this project. I'm also grateful to internal support for students and the National Isotope Program for providing americium, the americium that you saw in this talk. And with that, I'll just conclude and take any questions that you might have.
Thank you, Stosh. Great presentation. We'll start with Uwe Bergman. Uwe, you had a question?
Oh yeah, hi Stosh. It was really a fantastic talk. Thank you. I learned more in this 45 minutes or 1 hour than in many previous meetings. I have a question, but I mean, this concept is really beautiful. And I think you showed also this concept of having a numerator and a denominator, and having the spatial, what I call spatial overlap, the orbital overlap, and then but also the energy matching, and that you can, by using oxidation state, you can kind of separate the two contributions somewhat. My question is, are they not? They must be somehow intertwined, though. My feeling is. So you when you change the one, you do change the other, and maybe you can comment a little bit more on that.
Yeah, you do change the other, and I think that the nice example is if you only thought about the numerator, when you increase the oxidation state, you're going to collapse those f orbitals even more. So you would predict, and we've run these calculations where you see that the orbitals are getting more contracted and more contracted and more contracted, but the covalency is turning on for the 5Fs. And that's just counterintuitive. The only way that can happen is with the energy match. And the same thing is true, we studied transition metal tetraoxos, the heebie-jeebies out of these things with Joe Bradley. Jerry, you'll remember that. When you think just about transition metals, as you go down the periodic table, you're going to make the denominator less and less energy matched. But that's not important for the d orbitals because the spatial overlap term is so large. But you're right, you can't say that it's the only contributor. You have to consider both, but I think the f orbitals are just unique because they are core-like.
And so the d, if you were considering, let's say, 3D metals and then d orbitals, that situation would be quite different.
It's the opposite, yeah.
Overlap would always be a much more dominating factor. Is that what you're saying?
I believe that for d orbitals, the overlap term is the most important contributor. Exactly. Yeah.
Thank you.
Thanks, Uwe.
Okay, earlier Christina asked a question from in a car. We have a question from Bianca who's on a train.
Oh, good.
And because the internet might be problematic, I'll ask for her.
Okay.
And what other ligands could you think of or try that would switch the covalency for the americium-3?
Yeah. So that's a good question. I think the trick there is you want to get ligands whose orbitals are quite high in energy. I think if you could make an americium carbonyl, that's going to be very covalent. Neutral things that maybe an arene or a benzene 2-, those should turn on covalency with americium. The problem is they're really, really challenging to make. They don't exist yet. But I think the idea is to get the orbitals of the ligand as high as possible.